On April 28, 1988, Aloha Airlines Flight 243 took off from Hilo, Hawaii, bound for Honolulu. What began as a routine inter-island flight across paradise would soon turn into one of aviation's most terrifying and pivotal incidents. At 24,000 feet, without warning, a massive section of the Boeing 737's fuselage suddenly ripped away. The serene Hawaiian sky transformed into a vortex of unimaginable forces, exposing passengers to the brutal realities of explosive decompression. This wasn't a sudden mechanical failure, but the culmination of an insidious degradation, a silent battle waged over years within the very fabric of the aircraft. Remarkably, despite the catastrophic structural damage and the immediate loss of a flight attendant, the aircraft remained controllable. The pilots, Captain Robert Skornsteimer and First Officer Madeline Nini Tompkins, faced an unprecedented emergency. With debris streaming past, wind roaring through the open cabin, and a gaping hole where the roof once was, they initiated an emergency descent. Their skill and composure allowed them to guide the crippled Boeing 737 to an improbable landing at Kahului Airport, Maui, saving the lives of 94 passengers and crew. It was a miracle, but one that demanded a deeper understanding of its origins. The aircraft involved, a Boeing 737-200 with registration in 73711, named Queen Liliuokalani, had been in service for 19 years. For nearly 2 decades, this specific airframe had diligently ferried passengers across the Hawaiian archipelago. While appearing outwardly sound, the true story of its aging was etched into its metal at a microscopic level. It wasn't its age in years that was the primary concern, but rather the sheer number of operational cycles it had endured, a critical metric often overlooked in early aviation maintenance philosophies, and central to this disaster. Aloha Airlines specialized in short-haul inter-island flights. Unlike long-haul aircraft that spend hours at cruising altitude, Flight 243's daily routine involved numerous takeoffs and landings. Each ascent to cruising altitude meant the cabin was pressurized, and each descent depressurized it. The research shows this particular aircraft had accumulated an astonishing 89,680 flights, equating to 35,160 flight hours. This high frequency of pressurization and depressurization cycles would prove to be a devastating factor in its structural integrity, exposing a hidden vulnerability in aircraft design and maintenance. This relentless cycle of pressurization and depressurization is known as cyclic loading. Every time a plane climbs, its cabin is pressurized to maintain a comfortable environment for passengers. When it descends, that pressure is released. This constant expansion and contraction of the fuselage skin exerts stress on the airframe, particularly around rivet holes and panel joints. Over thousands of cycles, even small, perfectly normal stresses can accumulate, leading to a phenomenon called metal fatigue. It's an invisible enemy that slowly degrades the material's strength, layer by microscopic layer, without overt warning. At a microscopic level, cyclic loading causes tiny cracks to form in the aluminum alloy skin of the fuselage. These microcracks are often initially imperceptible. With each subsequent flight cycle, the stress causes these cracks to propagate, growing larger and deeper. This slow, insidious process weakens the material from within, reducing its ability to withstand the very forces it was designed to endure. It's like bending a paperclip repeatedly. Eventually, it will break, not from one single forceful bend, but from the cumulative effect of many smaller, repeated stresses. Compounding the effects of cyclic loading was the corrosive environment of Hawaii. Constant exposure to salt spray and humid air accelerated the degradation of the fuselage's aluminum skin. Corrosion attacks the material, forming pits and weakening its surface. These corroded areas then become prime initiation sites for fatigue cracks. Once a crack forms in a corroded region, it propagates much faster than in pristine metal. For N73711, the tropical, marine environment acted as a silent accomplice, significantly accelerating the structural integrity's compromise. The fuselage of the Boeing 737-200, like many aircraft of its era, was constructed from multiple aluminum alloy sheets riveted together at lap joints. These joints are crucial structural elements, providing continuity and strength to the pressure vessel. On Flight 243, the failure originated in these lap joints. Specifically, multiple site fatigue fractures developed around the rivet holes within the upper rows of rivets. These tiny fractures, born from cyclic stress and exacerbated by corrosion, were the invisible fault lines that would ultimately tear the aircraft apart. Despite maintenance inspections, these critical fatigue cracks remained undetected. The lap joints were sealed with an adhesive to ensure airtight integrity and prevent moisture ingress. This sealant, while serving its intended purpose, inadvertently concealed the burgeoning cracks from visual inspection. The NTSB investigation would later conclude that the existing visual inspection program was inadequate for detecting such hidden damage. The cracks were too small to be seen with the naked eye and were obscured by the very material meant to protect the joints, creating a deadly illusion of safety. As Flight 243 reached its cruising altitude of 24,000 feet, the pressure differential between the pressurized cabin interior and the thin atmosphere outside was at its peak. The weakened lap joints, riddled with fatigue cracks, could no longer withstand this internal force. The structural failure began rapidly, likely initiating from one critical crack that suddenly propagated. This led to a cascading failure of adjacent rivet holes, causing an almost instantaneous rupture of the fuselage skin. The sudden loss of structural integrity was immediate and devastating, exposing the interior to the outside. The effect was dramatic. A massive 18-foot section of the fuselage roof and side, encompassing rows 5 through 7, was torn away. This wasn't a gentle peeling, but an explosive decompression, a violent, near-instantaneous equalization of pressure. Air, objects, and tragically, a flight attendant, were forcefully ejected from the aircraft. The sudden release of pressure and the incredible drag from the missing section severely compromised the aircraft's aerodynamic stability. The remaining structure was subjected to immense, unpredicted stresses, yet it miraculously held together, a testament to the original engineering's resilience. Amidst the chaos, Captain Skornsteimer and First Officer Tompkins reacted with incredible speed and precision. They immediately began an emergency descent, battling the effects of a partially depressurized cabin and severe aircraft buffeting. Communication with air traffic control was challenging due to the noise and loss of equipment. They managed to slow the aircraft, which helped reduce further tearing, and prepared for an emergency landing. Their composure under extreme duress, adhering to training, was paramount in navigating the severely damaged jet to a safe landing, saving nearly everyone on board. The National Transportation Safety Board, NTSB, immediately launched a thorough investigation. The wreckage, scattered across miles of ocean and gathered from the landed aircraft, provided crucial clues. Investigators focused intensely on the points of fracture, examining the rivet holes and the surrounding metal with microscopes. Their analysis confirmed widespread fatigue damage not just at the primary failure site, but also in other areas of the aircraft, indicating a systemic issue. The disaster highlighted a profound gap in understanding and managing the cumulative effects of an aircraft's operational life. The NTSB's final report pinpointed the primary cause, fatigue cracking of the fuselage skin, originating from multiple locations in the lap joints. This was significantly exacerbated by an inadequate inspection and maintenance program that failed to detect the damage. The report emphasized how the high number of pressurization cycles, far exceeding the original design's assumed limits for a 737, combined with corrosion, created the perfect storm. The visual inspection methods in place at the time simply could not identify the minute cracks forming under the sealant, leading to a false sense of security. Aloha Flight 243 became a stark wake-up call for the entire aviation industry. It directly led to a fundamental shift in maintenance regulations. The FAA issued new airworthiness directives, ADs, requiring enhanced inspections for aging aircraft, particularly focusing on lap joints and other critical stress areas. This was the genesis of the Aging Aircraft Program, which mandated more rigorous and frequent inspections for older airframes, moving beyond mere visual checks. The incident underscored the need to prioritize cumulative stress effects over simple calendar age. The disaster also profoundly influenced aircraft design philosophy. There was a renewed emphasis on damage tolerance design, which means an aircraft is designed to sustain a certain amount of damage without catastrophic failure. Furthermore, the incident spurred the widespread adoption of advanced non-destructive testing (NDT) methods. Techniques like eddy current inspection and ultrasonic testing, capable of detecting subsurface cracks invisible to the human eye, became standard practice. This allowed maintenance crews to identify and repair fatigue damage long before it could become a threat. The lessons learned from Aloha Airlines Flight 243 reshaped how we perceive and manage the integrity of aging aircraft. It cemented the understanding that the number of flight cycles, not just flight hours or calendar years, is a crucial indicator of an airframe's fatigue life. Every modern aircraft undergoes stringent maintenance schedules specifically tailored to address cyclic loading and environmental corrosion, with a strong focus on lap joints. The sacrifices made, particularly by flight attendant Clarabelle Lansing, were not in vain. They catalyzed improvements that have saved countless lives since. Today, thanks to the insights gained from Flight 243, aviation maintenance is a meticulous science, constantly seeking out the invisible threats of metal fatigue and corrosion. While the immediate horror of Aloha 243 unfolded in the Hawaiian sky, its true impact reverberates silently through every rigorous inspection, every ultrasonic scan, and every mandated airworthiness directive globally. It stands as a powerful reminder that in the demanding world of aviation, the most dangerous failures are often those that develop unseen, requiring unwavering vigilance to maintain the trust we place in flight.